So we can combine those two equations that we have come up with. We've got entropy of the universe is the system plus the surroundings, and then we've got the change in entropy for the surroundings is delta H over T. So hopefully I remember how I intended to do this. If we take delta S for the universe, that's going to be the change in entropy for the system, plus the change in entropy for the surroundings, which is negative delta H for the system over the temperature in Kelvin. You okay with that? Again, this is one of those derivations that I'm not going to make you reproduce, but I think it's helpful to see that these equations aren't coming out of nowhere. So then I've got a hint to myself, multiply by negative T. Okay, so that would give us negative T delta S of the universe is negative, T delta S for the system. And then multiplying this by negative T would give us plus delta H for the system. Did I do that right? Now, it would be really awesome if I could remember where I was going with this. So I'm going to look ahead to the next slide and see what it... Oh, well, that's kind of what we ended up with. Oh, yeah. So negative T delta S for the universe is negative T delta S for the system plus delta H for the system. Oops, sorry about that. So if this is just changing the order of these two terms. So we're not going to use the cis subscript anymore. We're just going to understand that quantities without a subscript refer to the system. If it's not referring to the system, it'll have a subscript indicating so. So what we call the Gibbs free energy, G, is equal to H minus T delta Ts, the temperature times the entropy. So H is enthalpy, T is temperature in kelvins, S is entropy. So then we can look at the change in Gibbs free energy at constant T. Delta G would equal delta H minus T delta S. I'm not putting a delta in front of the T because it's constant, it's not changing. Okay? So the change in Gibbs free energy for a process at constant temperature and pressure is proportional to the negative of delta S. So this can also be used as a criteria for spontaneity. It is also sometimes called the chemical potential. So it is analogous to mechanical potential energy. So just like with mechanical potential energy, think of a ball rolling down a hill. A spontaneous process is one that lowers the potential energy. A chemical spontaneous process is one that's going to lower the Gibbs free energy. So if delta G is less than 0, we've got a spontaneous process. Any questions? So the nice thing about delta G is we can calculate this just based on things referring to the system. We don't have to look at the entire universe. So that makes things a little more manageable. So we need delta H and we need delta S. So delta H information is found in chapter 6. Delta S we just looked at here in chapter 18. So here's a graph where we see this reaction of nitrogen plus hydrogen to form ammonia. So when we take those two pure gases, it will be spontaneous for them to react as long as Q is less than K. This is an equilibrium, and so we can look at the equilibrium constant. The reaction will change until Q is equal to K. If we started with pure ammonia, it would also be a spontaneous reaction for this to react in the reverse direction, again, until Q becomes equal to K. So both of these are spontaneous processes, and what we're graphing here on the y-axis is the free energy. So the free energy is becoming less as we get to the equilibrium state. So we're going to look at a couple of different cases where we're looking at different signs of H, S, and T. So if we have a negative delta H and a positive delta S. So negative delta H means that this is an exothermic reaction, it's releasing energy into the surroundings. Positive delta S means we have an increase in entropy. So both of these things suggest that this is going to be a spontaneous process. If delta H is negative and delta S is positive, since we're subtracting delta S, it doesn't matter what temperature this occurs at, delta G will always be negative. Make sense? There's no case in which we can have a positive delta G. So reaction with negative delta H, positive delta S will be spontaneous at all temperatures. An example here in this reaction, delta H is negative. How can we tell that delta S is positive? Increasing number of moles of gas. So we have increasing disorder, we can think of it that way, increasing number of places to put energy. What if delta H is positive and delta S is negative? So this is an endothermic process and the entropy is decreasing. So delta H is positive, delta S is negative. So then when we subtract a negative, this term is always going to be positive. Two positives, delta G is always going to be positive. So this type of reaction will be non-spontaneous at all temperatures. Here's another example using gases. What's wrong with this equation? It's not balanced and it's not possible to balance, because how can you turn oxygen into nitrogen? There we go. That's what it's supposed to be. I don't know about that. Here we're going from 3 moles of gas to 2 moles of gas, so that we can say that delta S is negative, right? Which is working against spontaneity. And then we also have, this is being an endothermic reaction, it's taking energy in. So there's no possible way that delta G can be negative. Case 3, both of these things are negative. An exothermic reaction, but a negative change in entropy. So this can be spontaneous at some temperatures and non-spontaneous at other temperatures. So delta H is negative, delta S is also negative. So delta S is working against spontaneity, but it's the relative sizes of these that are going to affect whether it's spontaneous or not. If T is large, then we're going to get a large negative component here, and a large positive component. Yeah, all those negative signs, right? We're subtracting a negative, so that's positive. A high temperature will make this positive term larger, and if that's larger than the negative delta H, then we have a non-spontaneous process with delta G being greater than 0. At lower temperatures, this term becomes smaller and it will be a spontaneous process. So spontaneous at low temperatures, non-spontaneous at high temperatures. Any questions? What if both of the terms are positive? Endothermic process, positive change in entropy. So now this is positive. When T is large, then we're subtracting a large positive term that's going to contribute to spontaneity. And this needs to be larger than delta H in order for us to have a negative delta G. So at low temperatures, this reaction will be non-spontaneous, and at high temperatures, it will be spontaneous. So this kind of makes sense, at least in my odd brain. Here we've got delta H is positive. This is an endothermic reaction. And we learned about equilibrium and Le Chatelier's principle that for an endothermic process, if you put energy into it, that's going to promote the products, right? In this situation, delta H is negative, and so removing energy would promote formation of the products. So those two things go along with each other. So when delta H and delta S have the same sign, the spontaneity will depend on the temperature. If the signs are not the same, then it will be spontaneous or non-spontaneous, depending on at all temperatures. So we can find the temperature at which spontaneity changes by setting delta G equal to 0 and solving for T. Because 0 is the point where delta G goes from negative to positive. Any questions? Consider the reaction. We're given delta H and delta S. Calculate the Gibbs free energy change at 25 degrees Celsius and determine whether the reaction is spontaneous. Does delta G become more negative or more positive as the temperature increases? Well, let's just answer the first question first. What is the equation for delta G? Delta H minus T delta S. So we have delta H and we have delta S. This is in joules per Kelvin. This is in kilojoules. It's not specifying what unit we should use for delta G, but we need to pick one, joules or kilojoules. I'm going to pick kilojoules. And then temperature is given in Celsius, as is typical, but we need it in what unit? Kelvin. So 25 degrees Celsius plus 273 would be 298 Kelvin. So delta H minus 137.5 kilojoules minus temperature in Kelvin, 298 Kelvin, times delta S, which is negative 120.5 joules per Kelvin. But wait, that needs to be in kilojoules. So in kilojoules, that's going to be 0.1205 kilojoules per Kelvin. Some of you are still a little rusty on your conversions or kilos. Write it out if you find that you're getting them backwards. Okay, so negative 137.5 minus 298 times negative 0.1205. I'm getting negative 101.6. And the units there are kilojoules. So the kelvins cancel out. Units are your friends. The units on delta S suggest that we need a temperature term in there, right? And that can help us to remember what the equation is. So is this reaction spontaneous? Yes, it is. Because delta G is negative. You can think of delta G as a negative or a chemical potential, and lowering the chemical potential, like lowering the physical potential energy, is going to be spontaneous. Is this going to become more negative or more positive as the temperature increases? So, yeah, it's going to become more positive. So this term, as temperature increases, as T goes up, then we're subtracting a larger number. I don't know what I'm doing here. This term goes up. Subtracting a larger number gives us more negative. More negative at high temperature. I don't remember what you guys said. You said positive. As the temperature increases, no, you were right. I was testing you. No, I'm not a morning person. Aren't negative signs the worst? You really have to think through this. So as the temperature increases, this term gets bigger. I'm subtracting a negative that's larger, which is adding a positive, right? So this is going to be taking away from the negative delta G. Any questions? That didn't go very well. Yes?
So if our end result is positive and as temperature goes higher, would it still be positive? Or would it stay?
It would still be that it was becoming more positive at higher temperatures. The direction would stay the same. So that, I think, I found that confusing. What's another way that we could answer this question?
Just add a bigger number.
We could just stick a different temperature in there,
Yeah.
right?
That's what I did.
So let's just stick 1,000, because that would make the math easy, right? So minus 137.5 minus 1,000 times negative 0.1205, right? And this is something that's good to do on a test when you kind of don't trust your brain anymore. And so that's giving me minus 17. So that's becoming less negative, which is more positive.